Hey guys, it's Amanda from the College of Science. Welcome to the watch party. The Perseverance is about to land, or has already landed. What I want to do is tell you guys a little bit about why we're studying Mars and how we can use Earth as an analog for Mars. So Earth is able to tell us a story because of the rocks it holds. I'm classically trained as a geologist, and if you go out, any single rock that you pick up tells a unique story. You start taking all of those rocks, put it together, you can tell the story of the Earth. The present is the key to the past. So the wind blows today. The wind blew millions of years ago. The Earth is spinning on its axis. The Earth didn't all of a sudden change its rotation. The Earth has always spun the same way. We use those as keys, so the present is the key to the past, keys to tell the story of what happened in the past. And Mars is part of that story. But how are rocks currently made? So you guys have all heard about the rock cycle, and we have three main rocks: igneous rocks, metamorphic rocks, and sedimentary rocks. One of the main reasons they're going to the Jezero crater is because they think they might be able to find life there. Of these three rocks, only one of them is going to tell us the presence of life, and it has the most information in terms of what's going on the surface of Mars. So let's look at these rocks in detail. Sedimentary rocks. You have two types. You have sedimentary rocks that are made of clasts, all different things coming down, getting cemented together, bada boom, bada bing. The next type is chemical. Chemical sedimentary rocks. You have dissolving materials, it precipitates out, and you have something like salt or gypsum. Those are the ones that can preserve life. The image on the screen is, what do you think? Does it look like roots? Does it look like burrows? Does it look like claw scrapes? Those are actually worm burrows. And we can tell how old they are, specifically what they were eating, how they traveled, what kind of environment they lived in, just by looking at this one rock. So sedimentary rocks are important, and we'll come back to these. But we have to tell the difference between the other rocks. So igneous rocks. Those are basically what all of the continents are made of. This is the starting point for all planets. Usually starting out as a molten ball flying through space. Then you have crystallization, and you start to make those igneous rocks. If we look at the composition of the Earth, if we think about the periodic table of elements, 8 of those elements make up 98% of the Earth. Only 8 of them. So those are really important, and we have to know those igneous rocks. That's kind of the foundation for when we're talking about these planets. And then we have to think about metamorphic rocks. Those, we're adding heat and pressure. They alter the rock's chemistry. They destroy all fossils. So metamorphic rocks do not have any fossils. But they tell us if there's plate tectonics active. The only way to make gneiss, and that's how you say the one in the bottom right corner, it is gneiss, that's high-grade metamorphic rock, is to have Himalayan scale mountains. Now, some of you might notice that we have these behind our Weber State. You go up on the trail, you find rocks that look like this. It's because Utah had Himalayan scale mountains millions of years ago. Some of it looks like bedding, so we have to know the difference between that. So if we find a sedimentary rock and a metamorphic rock, you can see the difference. So it's really important to understand your rocks. So do you think these processes are unique to Earth? You all know the solar system. We've got the sun, the rocky planets, the asteroid belt, and then the gaseous planets. Sorry, Pluto, we miss you, we love you, always. But the middle, the rocky planets, those are all made of those elements, right? Those 8 elements that we're talking about from the periodic table of elements. We're all in the same solar system. Gravity is affecting us the same way. So we have to think about these things when we're talking about Earth and other planets. Now, the foundations of Mars. We already know from satellite images, we've sent rovers up there, water is the main driving force for the topography, the way that the surface of Mars looks. It's red, that's great, but there's also features that have been washed down by water. So why does water move? How does it move? How does it erode? Part of sedimentary rocks is weathering and erosion. Where does water go? Hopefully at this point you know water doesn't move up. Water goes down. Okay, what does water bring with it? If you've been to the Mississippi, you know we call it the muddy Mississippi because it's full of mud. But if you've been down in southern Utah and seen a flash flood, you know that it carries much more material than mud. Mud plus rocks that are bigger than me. And does it only have to be water? I mean, we think of Mars having water doing this erosion, but the ice caps aren't actually ice, they're frozen carbon dioxide. So can you have flowing carbon dioxide? Or what about methane? Anything that's fluid, could that be present on Mars? Either way, if you have a flowing fluid, okay, so we're going to say water in this case, it produces very distinctive features on the surface of a planet. Now, this is an image of Mars and Earth. Do we see the similarities? Can you tell me which one is Mars and which one is Earth? It becomes a little bit difficult, right? We find these on Earth. So the one on the right is Mars, the one on the left is Earth, because there is no current water flowing on Mars. So it's being eroded and there's not new erosion occurring. So it's just wind blasting everything. That's why it looks kind of smooth. What about this image? Is this Mars or is this Earth? If you've been to Death Valley, you might think, it looks a little bit Death Valley-ish. If you've been to Mars, you should come talk to me. But you would notice that this is actually from Mars. But these features, very distinctive of flowing fluid. What about this image? Okay, the craters kind of give it away, but we call this a dendritic drainage system. You have to have topography, right? Topography being mountains and valleys, in order for that particular type of drainage system to form. Here on Earth, we have mountains because of plate tectonics. You have one plate slamming into another one and pushing everything up. So does Mars have plate tectonics? And then we get down to the nitty-gritty. So we were at satellite view. Now we're going down into actual rock details. How do you round a rock? If I were to give you a rock that I just smashed with a hammer, how would you round it? Most of you, as children, have had your rock tumbler, right? You ran it for 2 weeks and decided you were tired of it. But that's what happens in nature. The only way to round rocks is to tumble it down streams using water. It hits each other, knocking off those edges. That's the only way to make these rocks. Now, you can see Mars and Earth have exactly the same type of rocks, at least in terms of rounding and in terms of sorting. So sorting means there's a bunch of grains the same size, that's really well sorted, or you have a bunch of grains that are all different sizes, that's poorly sorted. If it's really well sorted, you get something like mudstone. Again, this image, go down to southern Utah. This is exactly what it looks like, but this is Mars. This is mudstone that was formed on Mars. Low energy, it's got very flat beds. And the only way to make that is in a lake. Huge flat beds of very flat sediment that's made of mud. You're talking a lake, very low energy environment. Does this look like a rock that you've seen, especially along the Wasatch Front? The gray rock. If you've been up Ogden, pretty much any canyon you go up, there are gray rocks. This is limestone. This is a particularly interesting rock when we're talking about Mars because limestone only forms in water. This type of limestone would only form at the bottom of an ocean. So we're not only talking small bodies of standing water or fluid on Mars, we're talking oceans of water that used to be on Mars. And you look at the landscape, there's no water now, but all of this topography, all of this rounding, all of these rocks absolutely tell that there had to have been some sort of flowing water, topography, something was going on very early in Mars's history.